Hello, dear students. I am Samir Velankar. I welcome all of you to this third video on the topic graph color problem. In the previous video, we saw very important function called color. This color function will check whether kth vertex, k is the vertex number, whether kth vertex can it be colored with ith color, I is the color. And what it does, it checks all the previously colored vertices. I told you in the earlier video, if we are coloring kth vertex at the moment, then surely we have colored 1 to k minus 1 vertices already. So we browse through, we go through all the previously colored vertices, and to each vertex we ask, is the current vertex that we are coloring, is it neighbor of the jth vertex? If it is adjacent to the jth vertex and the previously colored vertex, that is jth vertex, is having same color as I, then return false. So adjacent vertices cannot have same color. And if all these vertices in the for loop have no trouble whatsoever, then we return true, that you can color kth vertex with ith color. Now in this video, I will tell you how graph color function works. Check that graph color is a recursive function. So what I will do is, in down over here, I will show GC running. GC stands for graph color. And just imagine that we are storing our result in X array, isn't it? In the earlier video, I told that colors of these vertices are going to be stored by the X array. And X array is having 4 elements in this example because there are 4 vertices. And each element of X array will store the color number of that corresponding vertex. Now, this graph color function will be called from main as graph color 1. That means the parameter k that will be passed is 1. It's completely a very clear idea because we want to color all vertices, but we will start coloring always the first vertex, isn't it? So at the moment we have kept k as 1 and we are about to color this first vertex. Rather, we are talking about the first element of the X array and we are interested in knowing which color should be given to the first vertex. Now tell me, aren't there n colors given? Yes, number of colors are n. Then question is, which color you should give to this first vertex? Isn't it? That's the question. Hello. You can give any of the colors 1 to n, isn't it? In fact, that is what we have to check, that which out of these n colors can be given to the kth vertex. So I hope you understand the for loop which I am pointing here on the left hand side. I is going from 1 to n. And what is n? N are the number of colors. So while coloring the kth vertex, while coloring this kth vertex, we will first ask, kth vertex, can it be colored with first color? If yes, better color it. If no, then try for the second color because we are in the for loop and I will vary from 1 to n. If second color is also not suitable, then check the third color and this goes on, isn't it? So in the recursive function, GC at the bottom of the screen I am showing, graph color has started with 1. That means k is 1 at the moment, isn't it? And we are about to color the kth vertex, that is first vertex. So the loop begins with I equal to 1. The for loop begins with I equal to 1. And when I is 1, check this for loop. We are going to immediately contact the color function and color function will check, can we color first vertex with first color? Now, this is a very senseless question. You can always color the first vertex with first color because at the moment no other vertices are really colored. So color function is definitely going to return true. And therefore this if will be true, isn't it? Then these lines written in the if will run and the statement which I am pointing to right now makes xk equal to 1 because I is 1. So xk, this element xk at the bottom of the screen becomes 1. That means we have really colored the first vertex with color 1. I hope you are understanding. So what next? what is the next thing we should do? Now we have completed this statement. What does this statement mean? Kth vertex is colored with ith color. So we have successfully completed coloring the kth vertex. Now the next if statement is about if k is equal to v. Now k is the vertex that we were coloring. K was 1 and number of vertices are 4. So in fact what this if is checking, is that which vertex did you color? Was it the last vertex? Come on, if you have colored the last vertex, then you have found out the solution. If this k was 4, then all vertices are colored and we can print the solution. But right now, the vertex that we have colored is just the first vertex, isn't it? So this if is false and else runs and graph color is recursively called. The same function is called again with k plus 1. So here at the bottom of the screen, I am showing graph color calls graph color with parameter 2. That means now the value of k is going to be 2. So we are about to color the second vertex now, isn't it? So definitely now k is 2. What that means, in the array, we are now trying to fill second element k is 2 and we would like to know which color you should give to this second vertex. So new function has begun. Let's run this recursively. Well, the call is graph color 2. K is 2, remember. Let's run this. We want to color the second vertex, isn't it? Which color you should give to this second vertex? Which color? Don't say directly 2. You always start coloring this with 1, but color function will shout you can't color it with 1. You say, okay, if I can't color it with first color, I'll try second color, then third color. So are you understanding the for loop? While coloring kth vertex, always try color number 1. If not, then try next color, I plus plus. If not, then try next color. So in this function at the bottom of the screen, gc2 graph color 2, I will start the for loop with I equal to 1. Interesting. Now we are going to ask, can we color second vertex with first color, and color function will return false. Definitely it will return false because you can't give this second vertex. You can't give color number 1 because first vertex is already colored with color number 1 and they are adjacent. So color function rigorously will test, are the adjacent vertices having same color 1? Yes, so it will return false. And as color function has returned false, this entire if is not going to run. Check the scope of the if. This if runs up to this point, isn't it? So what happens if the if doesn't run? Obviously the for repeats. The next point is the for, and the for is going to make I equal to 2. The concept is, at the bottom of the screen I am showing, the concept is I equal to 1. First color was not suitable for the second vertex. So you test, can second vertex be colored with the second color? Isn't it so? Yes. So now again for I equal to 2, color function is called, and the color function will ask, can second vertex be colored with second color? And of course it can be colored. It will return true. You watch, if you color this second vertex, check this, if you color this second vertex with second color, it's not going to obstruct the previously colored vertices. So as color function has returned true, the line xk equal to I runs. That means xk here at the bottom of the screen, xk becomes equal to 2. So we have colored second vertex with color number 2. After that, we will ask the next question. Check what I am underlining. Was k equal to last vertex? But k was just 2, second vertex, and we have to color 4 vertices. Then this if statement is false. And else runs and graph color executes again with graph color 3. So we are about to color the third vertex. I guess you have followed all the ifs and else. But if you have seen the earlier video of n queen problem, you would see that teacher is actually running a cassette and same tape is played again, because instead of the name color over here, we had the name called place, and instead of recursive call here graph color, we had n queen k plus 1. For the rest of the things, the entire structure of this function is absolutely same, isn't it? Now just imagine graph color 3 runs with k equal to 3. With k equal to 3, then we will test the first color I is 1, and I is 1 is not suitable, so we will check I is 2. Not suitable, then we will check I is 3. Yes, 3 is suitable. So we will color this third vertex. The third vertex will be colored with color number 3. And then GC is going to call graph color is going to call graph color 4, isn't it? Where k is 4. So the new function has started. That means we have already colored first 3 vertices with color 1, 2 and 3. And now k is 4. For k equal to 4, we will again try the first color. But first color is not suitable because the fourth vertex, if colored with 1, will obstruct the neighboring vertex which is already colored with 1. So we will try color number 2, and color number 2 is okay. Color function will return true. Hence, we will make xk, fourth element xk equal to 2. And now comes this fun part. K is equal to V. You see, just now you have colored fourth vertex and number of vertices were 4. Then it's time to print the solution. Printing the solution is nothing but printing the entire X array, isn't it? So in short, if I'll clean the slate, in short, if you see what is the summary of graph color function and nqueen problem is that if you are trying to color kth vertex, then try color number 1, then color number 2, next color up to n colors. If kth vertex can be colored with ith color, you can give color I to vertex k, then better color it. Make xk equal to I. And then ask, are all the vertices colored? Which vertex did you color right now? Was k equal to V? Then all the vertices are colored. Then print entire X array. But if all the vertices are not colored, then call graph color for coloring next vertex. Next vertex will be k plus 1. Isn't it? That's how graph color function summary can be seen. And we are trying all colors. So all this material is written in the for loop while coloring kth vertex, try all colors. I hope you have understood summary of the graph color function. And in the next video, when we come back, we are going to see more backtracking algorithms. Very interesting backtracking algorithm is Hamiltonian cycle. Hamiltonian cycle. And one more called traveling salesman problem can be solved using backtracking. All these things we will see in the later videos. Thank you very much.